the classroom, we are done with the flow net. We are done with the flow problem. So we're going to move on to the new subject. And today we'll talk about the settlement. The settlement in the soil. Okay, we have a ground surface like this. This is the site that we want to build the structure. And so we are building a factory. We're building a very big factory. Then, because of the weight of this structure, the soil will be compressed a little bit, right? And we don't know how much yet, but eventually, because we are adding additional force in the ground surface, it's gonna settle down. And this is the settlement. So you can think that the soil, like to a certain depth, or like a thick soil layer is getting compressed because of the additional force or the additional weight of this structure. So when you look at the soil mass here, before there will be an effective stress, the vertical and the horizontal effective stress. So let's assume there is no structure. Then effective stress, the vertical effective stress will be what? The submerged, no, let's say submerged. Yes, it's above the ground surface then, groundwater table. And we're going to use the total density G and Z, right? And horizontal stress will be what? N times vertical effective stress. Right. There was the original stress condition in the soil. And this will increase as you go deeper. And suddenly you're building a structure that added additional stress to the soil mass, which will be use the blue one, that's going to be delta sigma. So this delta sigma is caused by the weight of the upper structure. That's artificially increased. So then this settlement will be influenced by the amount of the stress increased. Right? So if we just think from our gut feeling, the settlement will be a function of delta sigma. If you add like very high polarized building, then it's gonna cause more settlement. If you have maybe two-story building, then it's going to cause less settlement than the high-rise building. Right? Then what else? What will be the function? What's affecting the settlement? Besides the additional stress, the type, soil type, right? And we say that compressibility. How well soil is compressed for a given loading. When you compare very rich soil to the soft soil will cause more sediment because it's more compressible. And rigid soil with maybe boulder, with the gravel, it's gonna compress less than the soft soil. So compressibility is the one parameter. It actually is a chemical property that represents the soil compressibility. And this compressibility is on presence of water. Soil type. initial void ratio. Let's remember that when we did the metabolism test, we have a same soil, and when we add a little bit of the water, it now becomes plastic. And when you increase the amount of water you're adding, so it becomes like approaching to the equilibrium state, then soil becomes more softer, right? Much softer. So that's gonna give you higher compressibility comparing to the case when you have lower water content. Right? So presence of the water will affect the final this parameter compressibility. And the soil type, if you have more clay content in the soil, then it's going to be more compressible. Right? Initial void ratio, how well it's compacted. Right? Surely they're going to compact before, prior to the construction, right, to make it flat. So they're going to compact it with the compactor, and depending on the dry density and relative compaction, if you remember the definition of relative compaction, what's the definition of the relative compaction? Density, maximum dry density. To what? Natural dry density. Right? Diffuse dry density over laboratory driven maximum dry density times something will give you the relative. So initial void ratio, if it's lower initial void ratio, means it's more compacted. So we'll give you less sediment. Right? So there are several parameters that influencing the compressibility. So first question that we have to shoot is, can we predict the sediment? How much sediment will occur when you put this amount of weight on the soil ground? That will be one question. How much? And this will affect the serviceability. Until it can function correctly and properly. And second is this is about the timing of the sediment. How long it will take until it starts the sediment. So settlement, maybe it can happen instantaneously. When you apply the load, it can compress within a second or within a day. They can be considered an instant sediment. But if it's very soft, but some weird clay, maybe with the sediment that can take about several years. So then if you have a, then that means you will have to wait until you can enter the structure, or until you can construct more stories over the top of the structure. So the timing, all the question about how fast the sediment will occur is also important part, because it's going to increase the cost. So we have to wait. The construction company will have to wait until the sediment is over. Then they're going to continue their project. So this will affect the overall cost. So this is a zoom view of the soil net. So if we look at the grain size scale of the soil mass, then we can idealize the soil mass with this configuration. So the soil is contained in the soil bucket, and we apply the stress. Right? Here the sigma naught is the initial stress by the over the soil. And because of the stress increment, you have a delta sigma develop. So that's the whole stress is going to increase. So imagine that we have a loading plate, and in this loading plate we will start with increasing the vertical stress. And when this stress increment is small, then you will develop a very small amount of deformation. Then the loading plate will go down by a small bit, so that can be replaced by this delta E, the epsilon strain. And this deformation is actually caused by the deformation of the grain itself. So when you remove this delta sigma, what will happen? Then it's going to go back to the deformation. Right? So this deformation is recoverable. So we can say that it's elastic deformation. So we can go back to the original position. When you increase this delta sigma to a certain point, so that you're applying a large amount of stress increment, then what will happen? So this soil mass is going to find some place they can cope with this large amount of stress. So that means that the particle will move and rearrange themselves to be to sustain, to reduce this large amount of stressing. Say that this kind of deformation is because of the particle rearrangement. The particle itself will find another place to be able to reduce the large amount of the stress increment. And when you remove this delta sigma, in this case, does it go back to the original position? Say that when you're in the stress on the top, now the particles are settled more and they find another place. So when you remove it, still it's going to stay in the same place. Right? So this deformation is not and it's not elastic, so hold it. So then we'll talk about the deformation of the set. This was about dry soil. analogy that I wrote before. So in the syringe, there's a soil mass which is fully saturated, and I'm applying the stress while I'm blocking the bottom hole. Then what happens? To the stress. Because the water is not, water is very stiff. It's much stiffer than the soil. So when you increase the delta sigma here, you increase the molecular stress, then water takes up the most of the stress. Water takes up the most of delta sigma. So delta sigma transfers to the pore pressure. So I have a soil mass, fully saturated soil, and when I push it, soil skeleton doesn't feel anything because water is feeling good and resisting all the stressing. Because the water drainage is now allowed in this case. So actually, this is the we can go on here. Simplify is this figure is string analogy. In this case, we have sigma naught, and there's a hole in the valve. In this case, so we have a here the spring is representing the solar skeleton thickness. So this spring is a solar skeleton, and in the chamber is a full of water. When you increase stress by delta sigma, because this hole is closed, so the water pressure will increase. So sigma effective stress, initially there's a pore pressure U naught and total stress sigma naught. So effective stress was sigma naught minus U naught, right? Because effective stress is total stress minus pore pressure. When delta sigma is applied, what happens to the pore pressure? Pore pressure will increase by delta sigma. Right? What about the total stress? Total stress is also increased by delta sigma, right? Here, that plus delta sigma, and total stress also increased by delta sigma. So when you calculate the effective stress, total stress minus pore pressure, so this delta sigma will cancel out each other. So you have say sigma naught minus So if the effective stress didn't change, it stayed constant because the water pressure was taking off all the stress. this case, the water drain gauge, now the hole is open at the top loading head. When you increase the stress, this delta sigma, because the pressure is, the hole pressure will increase, so that the water will try to escape. Right? So water will be squeezed out while the soil skeleton gets compressed. So think about the pore pressure. So initially, pore pressure was, and when you apply the delta sigma, here delta sigma is applied. What happens to pore pressure? Pore pressure will increase by how much? By delta sigma. Then what will happen? Because now the hole is open, so the water can escape. So it's going to increase like this. And so the water pressure will drop, and it's going to go back to the original value. U naught. And this will be the case for the sand. This dropping rate, pore pressure decrease, the rate of the pore pressure decreases really fast because the sand has a lot of pore size, the water gas can be squeezed out very quickly. If you think about the clay, one of the permeability of the clay, it has very low permeability. So it's high. So clay has low K permeability, low permeability, and sand has high permeability. So, in case of sand, the water will squeeze instantaneously, so that the pore pressure reduction rate, maybe it may take about 1 hour, 2 hours, and less than several days. But in case of clay, this pore pressure reduction, or we say that pore pressure dissipation, can take about years. So we're going to think about the clay, and we apply the over the stress. Initially, before total stress was sigma naught, and pore pressure was also initial value u naught. So the effective stress, sigma prime naught, was sigma naught. When delta sigma is applied, the total stress will increase by delta sigma. And what happens to the effect of the pore pressure? Pore pressure will be also instantaneously increase by the amount of the stress be squeezed out. So then the change in the total stress will be the same. Stress. And what about the pore pressure? It's gonna spike. It will spike when right after the delta sigma is applied. 5 is delta sigma, and then because the water can escape, so that it's gonna decrease to the original value. Right? So it will go down to then you calculate the effective stress. To the effective stress. Effective stress has increased by delta sigma. Right? So, summary again is delta sigma excess open. It's gonna be something. So that it becomes the initial value. And while this pore pressure is decreased, effective stress is increased. So consolidation is defined as a compression process or saturated soil is controlled by the rate of recess dissipation. So then the rate of recess dissipation, so how much water can escape or how fast water can escape is controlled by what? K, permeability. So permeability will define and determine the rate of